Okay, let's get started. First of all, I say several people here. Thank you for being here. So next Wednesday, we will have the midterm, and I already gave you guidelines and also the rules for the midterm. So today we will keep talking about access control. So Monday we talked about several different access control models. So today we will actually keep talking about access control models, and but we will start with something simpler than access control models. We will talk about confidentiality policies. So those confidentiality policies, they do not strictly belong to any access control model, but they are related. So confidentiality policies, as the name suggests, they emphasize confidentiality. So they do not care that much about integrity, availability, or other security properties. They emphasize confidentiality. So because they only emphasize confidentiality, you can say that it may not be very comprehensive. So they may not be very useful in all scenarios. However, confidentiality, as we discussed in crypto, confidentiality is like the number one, the most important property when it comes to security. Thousands of years ago, when we talk about security, even though we don't have the word security, but it probably only means confidentiality. So those policies are very important because what they can provide, and also in the history, how they help to develop other concepts of security. So one of the most important confidentiality model is called the Bear-Lapadula model, and named after the researchers behind this model. So this is one of the classic confidentiality policy. So this policy basically provide a military style classification, and it has influenced the development of many other models, also influenced the design of our computer security techniques. So confidentiality policy, also we can call it an information flow policy, prevents unauthorized disclosure of information. That's the meaning of confidentiality. So unauthorized changes of information is not as important as disclosure in this model. For example, in a military scenario, let's say we have in Navy scenario, so the Navy want to keep confidential the date on which a ship will sail, right? That's top secret. So if the date is changed, maybe the redundancy in the system, there could be a lot of redundancy copies of this date in the system. So they should catch that change, but it's not that important. More important is to prevent the enemies knows the date of the sailing, instead of make sure that all copies in our own system has the latest date, because that would be an integrity problem or availability problem. However, if this information is disclosed to enemy, obviously the enemy can attack us. So in this case, confidentiality is more important than availability and integrity. So the simplest type of confidentiality classification is a set of security clearance arranged in a kind of like a linear order. For example, in this, we have an example here. We have 4 different levels of confidentiality. The highest level is top secret, then there is secret, then there's confidential, then there is unclassified. From the names, you can see that this is very much like the military confidentiality classification we are using in real world. So the model of Beer-Napadula model is to prevent the information flowing from objects at a security classification higher than a subject's clearance to that subject. So like I said, that we have, in this example, we have 4 levels of confidentiality, from top secret to unclassified. Then we have 4 entities here, and they are people, they are subjects in this case. And those 4 people, each of them, they have a different clearance level. For example, Tom at the clearance level of top secret means Tom can say can have the access of all the objects that is labeled as top secret. For example, personnel files, we can label them as top secret. In email, we can label them as secret. Activity log, just confidential, and the telephone list will be unclassified. Everyone will be able to access. So in this example, let's say Claire has the clearance level of confidential. So Claire will be able to say activity log files and also telephone list files, but will not be able to say email files and personnel files, because those objects, they are at a higher security classification than Claire, the subject's clearance. Okay, so if we formally model this, a lot of books, especially security theory books, they will try to formally model this. So they will say there is a function ls is the security clearance of the subject S. So the L is the security clearance function. Then another function L, well, this is not the best way to write this. Probably it's better to write it with 2 different function names. But anyway, this book they use 1 name. The function L can also take object as input, and it will be the security classification of object O. Then the simple security condition, the very simple version, we will define subject S can only read the object O if and only if the subject's security clearance is higher or equal to the security classification of that object. In this class, we do not need to talk about the S has discretionary read access to O part. The most important is the first part of this. So this model should be easy to understand, because this is very close to our military model, and most people somehow, you know, in your life, you probably say top secret, secret, those in movies or some places. Okay, so is there any question so far? Okay, so this one seems easy to understand. However, there is a problem with this model. How do I get back? Okay, there is a problem with with this model. Let's say Claire here or Sandy here. Sandy is at the clearance level of secret. So Sandy can read the emails. And Sandy can also read or even write the activity logs or telephone list, right? Because those objects has a lower classification than Sandy's clearance level. So if in this case, Sandy is compromised, Sandy is not trustworthy, Sandy can read the electronic mail files and write them to the activity logs or telephone information, telephone list files. So when Sandy does that, it will make Claire, it will enable Claire and also Ursula to be able to read sensitive and secret information from emails, right? So in this case, the information flow actually flows from object at a higher security classification to lower classifications. So this is a leakage. So how do we prevent this? That's why in this bare Lapadula model, we have another property is called the star property. So the star property is a subject S can only write to an object O if and only if that object has a higher security classification than the subject's clearance, which means a subject cannot write top secret information to a lower secret file, but the subject will be able to write like a very let's unclassified data, read from unclassified data and write that to top secret. So you can say here, we do not care about the top secret files integrity that much. What we care about is the confidentiality of the top secret data will never be written into the unclassified. So this property in the model is called the star, called the star property. And it is proved that if the system follows the star property, the system will be secure, which means the system will never leak confidential information. Does that make sense? Okay, cool. Let's move forward. So, excuse me. We can also expand this bare Lapadula model by adding a set of categories to each security classification. In the previous example, we do not really have a category for the files. But so files there, we're talking about objects, right? So objects placed in multiple categories can have the kinds of information in all of those categories. So let me show you guys one example. Let's extend the previous model to the objects. We are going to label them with categories. In this case, we have, let's say, 3 categories, US, Europe, and NUC. So what is NUC here? I'm not sure. What is what can NUC stands for? North. Anyway, let's say this is a different region. We have US, we have Europe here. So then every object we can classify them into those three categories. But one object can be in multiple categories. Then the relationship between those categories, they form this kind of a relationship. So an object may belong to none of those three categories. The object could belong to one of those three categories. An object can belong to any two of those three categories, or one object can belong to all three categories. So those categories itself, they form this kind of relationship, and this relationship in logic is called lattice. Basically, this is a partially ordered set. So imagine at the beginning, we have a set of three regions: US, Europe, and NUC. So the power set of that set obviously will have 8 members, and all 8 members are here, including the empty set, right? The power set of that. And all the members in that power set, they form a lattice here. And this lattice is a partially ordered set. What does that mean? It means some of them, they have a ordering relationship. For example, the empty set, we can say is a member of the US, the set of with only US. And the set with only US is a subset of Europe and US. And the set of Europe and US is a subset of all three together, right? So if you look at this line, this path here, that's ordered. There is an order, there's a path. But some of those members, they do not really have a ordered relationship, like Europe or US. Europe doesn't belong to US. US is not a subset of Europe. So they do not really have this subset relationship. And as long as a partially ordered set has a unique least upper bound, like the three of them together, and a greatest lower bound, like the empty set, then we call this is a lattice in logic. Okay. So with the relationship between those categories, we can extend the Bell-LaPadula model to the security level of an object in that category. So now the security level is a 2-dimension representation. It's not a 1-dimension representation anymore. Let's say, for example, George is another guy, and George has the clearance into the security level of secret, NUC, and Europe. It only means that George can access the secret files that are labeled as NUC or Europe, or both of them. Then there is a document A. The document A is classified as confidential and in the category of NUC only. And let's say a document B is classified as secret in the categories of Europe and US. Document C is classified as secret and also in the categories of Europe. Okay. Then a security level L and C. L is the level, C is a category. We define that a security level LC dominates the security level of another security level. So we write this as LC dominates L prime, C prime. only and if only the security level of the second one is lower than the first one, and the category of the second one is a subset of the first one. Okay, so let's say George is the subject here. We would say George dominates doc A because George has this level of secret in two categories, UNC and Europe. Doc A is classified confidential at UNC. So secret George's clearance level is higher than the document's classification, security classification, and George's category is a superset of the document's category, which in plain English, which means George should be able to access doc A. In this model, we call George dominates doc A. However, if we look at another example, which is George and doc B. So doc B, so George has security clearance at two categories, UNC and Europe. However, the doc B is classified as secret, but not in the UNC Europe category. It's classified as in the Europe and US category. Okay. So which means even though George has the security clearance there, but he doesn't have the security clearance for this type, these categories of document. That's why George doesn't dominate doc B here. So George will not be able to read doc B. Doc C, you can see that the document security level is secret. The category is just Europe. So George will be able to read this document. I hope that makes sense. Okay. So obviously we can also extend this with the star property. So remember that we had the star property before, but the simple star property works with the simplified model where we only have one category. So now we have multiple categories, then we can extend the star property. But the basic idea is the same. And we can prove that as long as your system follow or meet this star property, your system will be secure. So besides confidentiality policies, in history, we also had some integrity policies. Okay. But I didn't plan to explain integrity policies. I just want to bring that up. However, the slides here is something wrong. I will update it later. Okay, so next we are going to talk about role-based access control, which is an access control model different from discretionary access control and the mandatory access control, which we talked this Monday. So in role-based access control, the subjects, besides subjects, objects, we introduce a new concept called role. Basically, it's role-based access control. So subjects are combined into roles according to their privileges in the organization. As you can imagine, this model has been used in most companies, bigger organizations, because in organizations, no matter it's commercial or nonprofit, we usually have the different positions, different roles. Like in the university, we have presidents, we have deans, we have teachers, we have students. They are those are roles. Those are not people. Then people have different roles, right? People may have multiple roles, and a row also may have many different people. So a row is basically a job function, and the permissions are not directly assigned to users. In previous access control matrix, stack MAC, we assign permissions or access rights directly to users. In RBAC, we don't do that. We assign them to roles other than directly to users. So a user can assume one or more roles within the organization, because of this, the model fit operational model of many organizations. This is widely used in our real lives. So this slide visualizes the relationship between roles, subjects, and permissions. So in this figure, we didn't really draw the objects. So in a long role-based access control model, we have subjects, which could be users. Then we have different permissions. You can say the permissions are a special access right. For example, Alice will have the database account. Alice will be able to use a database. Bob can also do that. Bob also has a WebSphere account. Carl has a Windows account, something like that. Right? Now we bring the concept of roles there. Now we created 3 roles. One is a database administrator, a web administrator, and a software developer. So the database administrator will need a Linux account and a database account. A web administrator will need a WebSphere account and also Windows account. And a software developer will have a Windows account and also Linux account. Then users, they are assigned to different roles. Anis can assume the role of database administrator and also the role of web administrator at the same time. Kyle can be a web administrator and a software developer at the same time. So what is good about this is people's role may change as their job may change. That's why this reflect our real world experience closely, because people, they change jobs. They get promotion, they leave the organization, they join new organizations. And that's why those permissions should not be directly assigned to users. The one layer of abstraction there, the role, can significantly help us simplify the relationship between them. Look at the figure here. How many relationships are there? How many lines are collecting those boxes together? There are many more than what we have in this figure, right? So adding a row, adding rows there, adding a lot of abstraction layer here simplifies their relationships. So actually the motivation for RBAC is because the user permission relationship is really difficult to manage when there are many users and many permissions, and it reflects it's an example that many problems in computer science can be solved by adding another layer of indirection. Okay. So when we use rows, there will be fewer collections between users and the permissions, or fewer relationships to manage. Potentially a decrease from a big O m times n, where m is the number of users, n is the number of permissions, to a linear one, just m plus n. Usually there are more users than rows and more objects than rows. And the rows are a useful level of abstraction because organizations, they operate based on rows. And also rows are likely to be more stable, excuse me, than users and resources. People come and go, people assume new roles, but the roles, they stay the same, the users, they change. And the resources also, they change very often, but the roles usually not. And with roles, we can effectively implement the principle of least privilege, where we only assign the privileges a row really need to that row. Okay. So finding the minimum set of necessary privileges or access rights is performed per row rather than per subject. So people may think, I mean, what is actually row? Row is basically grouping users together, right? If you think this way, it's very similar. So rows and groups, they are similar, but the difference is usually when we talk about groups, we're talking about the collection or the set of users. That's what we call a group. But row is not really about the group or set of users. Of course, there behind a row there is a set of users, but semantically, row is about the set of permissions, the set of access rights. It's not really about the users. What row really represents is, if you have this row, it means, if you assume this row, it means you have these permissions. So row is actually the collection of permissions. Also, RBAC in the model, it distinguishes traditional group from rows with a new concept called session. So basically, a session is a dynamic. It's dynamic. It's a period of time that allows activation of a subset of rows assigned to a user. That is called session. So RBAC has been very popular in big organizations. I think I have several slides talking about that later. So the model was published in like 1996, around that time, by Professor Ravi Sandhu. So Ravi Sandhu was a professor at George Mason. Now he's a professor at the University of Texas at San Antonio. I actually saw him 2 days ago. Yeah, we went to the same conference. So Ravi Sandhu is actually my academic grandfather. So basically, my PhD advisor's PhD advisor is Ravi Sandhu. And this is the original paper published almost 38 years ago. Rule-based access control models. So in this paper, Dr. Sandhu actually proposed 4 different RBAC models. We just call it RBAC 0, 1, 2, and 3. If you understand RBAC 0, then the other 3 would be easy to understand anyway. So the RBAC 0 is called the basic model, and the RBAC 1 extends the basic model and the row hierarchy there. RBAC 2 adds some constraints there. Then from the basic model, then we have RBAC 3, which combines row hierarchies and also constraints together. So RBAC model is like this. So this is basically from the paper. So RBAC 0 has 4 types of entities. So here we use uppercase, which means those are sets, right? So the first type of entities is users. That is a set that represent all the users. Then we have rows, all the rows, and also all the permissions, and a concept called a session, which basically is an activation of subset of rows. So user assignment is a many-to-many relationship. It assigns users to rows. It's a many-to-many many-to-many relation, means a user can assume multiple rows, and a row can have and also many users can assume the same row, right? So mathematically, if we use a set theory, it can be represented like this. So U times R, this is not the regular time, this is the set time, or I don't, sorry, I'm really tired today, so all of a sudden I don't remember what this is called in set. Decar product, I guess. Yeah. So basically, U times R here will create a huge set, and that set is basically any member of U and M, any member of U and any member of R can form a new member in the new set. And the UA is the UA user assignment is a subset of this. So this kind of like the whole set, and this is a subset of those. Then the permission assignment basically is also a many-to-many mapping between permissions and a row. So a row could have multiple permissions, like the web administrator I showed now. A web administrator can have the permission of using Linux, can have the permission to use WebSphere, right? And also permission can belong to multiple rows. The Linux permission, let's say, the Linux permission, the row of a software developer can have that. The row of database administrator can also have that, right? So this is also a many-to-many relationship. Then session is kind of like a function to activate the permissions. So there is a session function to activate users. Given a session, then we will say who is a user in this session. And also, given a session, we will say what are the roles that are activated for this user in this session. So the user do not necessarily assume all the roles in one session. So that is the basic entities in the RBank 0. So this is taken from the original paper. So session S must comply with UA and PA assignment. Let's say the roles this session has to be a subset of the user of that session and all the permissions, all the rows that user has. So basically, this means in a session, a user's rows, the activated rows of that user can only be a subset of what the user's rows are. Then the permissions of that session is basically the union. So this U here is not really the user set. This U here is the mathematical operation union. It's all the rows of that users combined together. So there is one user. That user has many different rows. Each row has different permissions, and the union of that permission will be the user's real permission under this session. I hope that makes sense. Then the RBank version 1 enhances RBank version 0 with row hierarchy. So now row has different. So previously when we define 0, we didn't really say the relationship between those rows, but the rows could have relationships. For example, the university will have president, we have dean, we have department chairs, and we have professors, right? There is a hierarchy there. So the row hierarchy captures that. And you can see that the row hierarchy, they form this kind of lattice here as well. Let's say we have a computer science office. Then that could be a row. Then there will be computer science undergraduate students. There could be computer engineering undergraduate students, and also computer science and engineering graduate student. Then there could be computer science and engineering undergraduate students, and those two are just a subset of this. Then the CSE students then will be the biggest set here. So they also form a lattice here. So the row hierarchies, the concepts, are based on the idea that subordinate job functions may have a subset of access right of a superior job function. A row inherits access rights of its descendant rows. So this is a formal model of RBank 1. We will skip this. If you are interested, you can read these mathematical representations. They are actually quite easy to understand, not very difficult. Then in RBank 2, we don't have a formal model. It was not formally written in the original paper, but the idea is to add constraint to RBank 0. The constraint could be many different things. For example, rows could be mutually exclusive. If, let's say, in a university architecture organization, if someone assumes the role of the department chair of computer science, they cannot assume the role of let's say manager of the chemistry department. Those are mutually exclusive roles. You can only take one job at a time. And then there could also be constraints on numbers. How many people can assume one role? How many permissions can a role have? And also there could be prerequisite constraints. If you want to assume this row, you have to assume another row before, right? So those are some examples I just explained. We will skip this one. So RBAC 3, the last model, basically combines all previous models together. And that is basically the RBAC model. So RBAC the model has been used everywhere. Our database systems use RBAC, enterprise security management use RBAC. Also, some operating systems, they also use RBAC. Obviously, Linux is not using this. And also, some research institute estimated the economic impact of RBAC back in 2000. They interviewed many software developers, many companies that use RBAC, and estimated that by 2006, 30 to 50% of the employees in service sectors would be managed by RBAC systems. It also estimated that the economic benefits of RBAC will be like 600 billions. So those just show how important RBAC is. Another analysis was performed in 2010. And they find that RBAC use actually rose to 40% in 2009, and it was estimated to be over 50% in 2010. So that's how important RBAC was, and because of that, least they standardized the RBAC back in 2001. So the standard has the core RBAC, hierarchical RBAC, static separation of duty, dynamic separation of duty, and this has been a very hot research area as well. And in 2007, another professor, Lee, from Purdue, actually criticized the standard. He believes the standard has some mistakes. Actually, I also saw him 2 days ago there. So access control models, especially RBAC, has been extensively studied. There is actually a ACM conference dedicated to access control models. It's called ACM segment. It's access control models and the technique. So in the last 20 years, the conference has been a value for research for RBAC and different access control models. However, recently, access control models is no longer a very hot topic because there have been a lot of research in that area. Many problems has been solved. As a community, we already made huge progress there. So right now, it's not a super hot area anymore. In the last 10 years, a new concept was proposed to, I would say, incorporate all previous access control models. And this is called the attribute-based access control. So we call it ABAC. So in ABAC, we specify properties in the form of attributes. And authorizations involves the evaluating predicates on attributes, and subjects, objects, even the environment can have their attributes. Then conditions on properties of both the subjects and objects can be enforced there. So ABAC is very flexible, or it's very expressive. It can specify many different rules and support all kinds of access control models. So technically, we can use attribute-based access control model to represent DAC, MAC, or RBAC concept. However, because it's very complicated, the model is much more complicated there than before. The performance cost will also be higher. The three main elements in ABAC are attributes, policies, and also architecture. So attributes are just the characteristics of subjects, objects, environment, and operations. So basically anything, they can have some attributes. For example, a subject can have attributes like the name, ID, job function. For example, the role in rollback now becomes an attribute of the subject. Let's say there is a person, we have his name, and he's a dean of the department. That dean of the department is his role, but in this case, it's actually the attribute of the subject. Then the object also can have names, titles. If it's a file, it can have a creation time. It can have ownership information. It just can be many different attributes. And also the environment can have attributes, like when, where do you try to access this data? What is the network security level when you access the data? The architecture specifies how access control is enforced. When a user submits an access request, the authorization decision, the access control decision, is governed by the policy, the subject's attributes, the object's attributes, and the environmental attributes. So because of this, you can say it can basically describe everything in access control, but it's also significantly more complex. So in such a system, what would the policy look like? So in previous example, we have access control metrics. So a policy can be read as a subject has the read or write or some kind of access rights to an object, right? That is what a policy, what a piece of policy reads like. But we didn't really use the word policy before. Now the policy can be much more complicated. It has the subject attributes, it has the object attributes, and also the environment's attribute or information. Let's say we have a database of movies. The policy may read like this. So the policy here is everyone can access movie rated as G. Okay, that's one policy. Everyone can do that. Then users of age 13 can access movies rated as PG-13. That's another policy. Users of age 17 can access movies rated as R. So the policy can be written like this. We are reading. So this policy actually specifies everything. let's say the first one is the subject's age. So we're trying to retrieve the attribute of the subject. If the subject's age is greater than 17, and the rating of the movie belongs to is one of those, is R, PG-13, or G, then this one is true, right? Which means this access should be granted. Otherwise, if the subject's age is younger than 13, is older than 13 and younger than 17, and the rating of the movie is PG-13 or G, then this should be granted, right? So that's why here we have the or relationship. Here we have the and relationship. Then the last one, which is actually the first policy here. Then everyone else, basically the kids who are younger than 13 years old, they will only be able to access the movie rated as G. So logically, this is what those three sentences look like. Combine them together. That's what it looked like. So policies can be combined into more complex rules. For example, limit access to new releases to premium memberships. Grant access if both rules are met, then we just have the previous policy P1, and we add. This is another add operation and of P2. Okay. So that is basically what attributes-based access control is. I feel you get the feeling that it covers all the access control models we have been talking about, but it's much more complicated. Okay, so last we talk a little bit about identity management. Identity management is related to access control, but it's not really access control. Identity management refers to maintaining identity independent of one's job titles, job duty. So access control privileges or locations. So those identities is not associated with our roles. Okay. So a digital identity is typically established based on a set of attributes. The attributes together comprise a unique user within a system or enterprise. Credentials gets associated with an identity, and access is based on credentials that identity possess. So different users, they may have identities in different network. So how do we use identities maintained by one organization to access or other systems? So that concept is called the identity federation. So now we are all familiar with a single sign-on. We only need to sign in a system once, then we can freely use a lot of services in a bigger organization. So those concepts are related to identity federation. It basically is collaborations among many different organizations. There were many identity management services. OpenID is one. I believe OpenID still exists. So how many of you heard of OpenID, or how many of you are still using OpenID? So many of those services, identity services, were not very successful commercially or in real world. In academia world, there is identity service called Orchard, ORCID, or maybe Orchid, ORCID or ORCHID. That provides an identity of each researcher. Then you can assign your publications, associate your publications with your online identity. Basically, it's not only just your name, right? Because many different researchers, they may have the same name. If you only use the name, then there were you cannot really separate who is who. That's why you have a unique ID, a unique identity. Then you can associate your publications with that Orchard number, and also associate your services. For example, you reviewed for some papers, then that service you can also associate with your ID. But besides that, identity management has not been super successful in our daily lives, I would say. Okay, so that's basically our access control modules. So the choice of access control model depends on the context. You can choose to use DAC, MAC, like the Linux. We are still using something similar to DAC. Then there are MAC implementations for Linux. In bigger organizations, we usually use RBAC, and then maybe in the future, even more complicated scenarios, we will just use ABAC. If you trying to choose what models to use, then you need to understand your limitations, your resource limitations, and your requirement. So consider the cost of implementation, maintenance. Federated identity allows for identity credentials to be used across different organizations. That's what I have for access control modules. Any questions today? Okay, if there are no questions, then I see you guys next Monday, which I think I plan to talk about database security. Okay, see you next week.